Do I want to add 3.7 to path?
Sorry, sorry again?
Add Python 3.7 to path.
Uh,
PET.
I think you don't need to do this manually. It should be done
Alright.
automatically for you.
Okay, install. Alright.
So after it installs, I want you to check in the start menu if you are able to write idle and you're able to see it. Did I show you idle last time, right? I believe I did.
I mean, you show me what it looks like. Yeah.
Okay, so
Yeah, I think it's downloaded. Is it downloaded? It should be downloaded. Yeah, Python. There you go.
okay.
Open. Oh wait. Wait, how? If I open it like that, I don't think this is correct.
Why?
Wait, let me share my screen. Screen to share. This is the screen one. Okay, you can see my screen, right?
Okay, yeah. So
Okay,
where is
yeah.
your?
This
No, that is not. No, it shouldn't be like that.
if I
Okay. Just search for idle. Yeah, this
this
is.
one.
Hmm.
All right. Okay.
So okay, no, wait. You have to write file. You have to go to file
Yeah.
here, file,
Wait.
and then open new
Okay.
new file,
Oh, okay, new file.
and then you write the code here. And then after,
Right. Yeah, because you run it here.
yes. So it will be
Yeah.
two screens. Yes. So of
So
course
what if
this
I
is not
actually?
as beautiful as
Yeah.
Replit.
Yeah. So does this work now? So I
Yep.
press F5.
F5 save.
Oh yeah, I need to save it to yeah, okay, I need to because I just saved to where is desktop? Just put on desktop. Okay.
You didn't put double quotation.
Oh yeah. Single also works, right?
I suppose double, but
Oh
try.
yeah, it works.
It works, right? Okay,
Yeah,
so
okay.
now,
Right.
okay, so any code you copy, it will work. You just need to
Yeah.
update the path to your game, and that's it. Okay, so we continue.
Right, okay, yeah.
Okay. So, Ashvin, do you need, I mean, are you exposed to other operating systems than Windows, or you didn't experience that yet?
I mean, I've seen Mac.
Okay, that's interesting. And what about Linux?
Linux. I don't think I've used Linux before.
No, I mean, not
My
not
memory.
in your life, but I mean in Lenovo.
Oh no. Oh, in Lenovo only Windows.
Windows.
Yeah. In
Okay.
Lenovo only Windows.
Okay. So, okay, let me then continue here.
So I think almost all I think of the Lenovo laptops use Windows.
Okay, that's interesting. So, is it your laptop is Lenovo or no?
Oh no, my laptop is MSI.
Aha, for gaming. Yeah. Okay.
Yeah,
Okay.
I'm using
Okay.
MSI. Yeah.
Okay. So, let us go back to recursion. Let me know. Do I need to remind you from the start, or we continue on the last thing that we have done?
I remember it's similar to multiplication.
Okay. So, can you understand this code in front of you?
Oh, okay. Let's see. Okay, def A B is 0 when B is more than 0. Okay, yeah.
You understand it?
So A is being B is being multiplied by A.
Okay. And do you
Okay.
understand why we need to decrement B?
Yeah, because if you don't, then it will never be less than 0.
Okay, so it will never stop. Am I right?
Yeah, it will never stop.
Okay. Do you understand why this kind of addition is considered A multiplied by B? Why is it like that?
B would be, in this case, in the following the arrows, B is 4. So B is the number of times you're you're adding.
You add. Okay, perfect.
Yeah.
Perfect. Okay. So may I understand from you why this kind of form mathematically we are able to represent it this way?
Okay. Equals A plus A times B. Oh yeah, okay. Yeah. Because you are basically because you're basically taking one A out from A times B. That's
Okay.
basically all you're doing. And then
Okay.
so you minus B by 1 because you're taking it out, so you minus it by 1 time.
Man, you are blessed with your brain. Really blessed. Yeah, really. But you are not blessed with something else, but I don't want to say it.
I know. Yeah.
I think both of us
I
know
know.
it. Okay.
Okay.
Okay. So let us talk about here then. Why they need to divide the code? So this is exactly the code that you have seen in the previous slide, but written in a different way. So we write it here in two different codes like that, two different portions. So we put an if statement, putting b equal 1, and then we write it this kind of return that try to simulate this specific mathematics. So you got the a here. This is exactly like that. And then you plus sign, and then a multiplied by b minus 1. So you call the same function again, but with a different parameters. So the a remains the same, but we, instead of multiplying it by b like that, we say minus 1. So it means that the function will keep calling itself until it reaches a certain condition. What is the condition that it will make this kind of self-calling stop? This is the condition. So the function will keep calling itself every time. But so, okay, now imagine how many b's here, how many a's here?
Well, including the dot, it's 5.
3, 4, 5. So b, assume it is 5. So every time, so we will start here, b equal 5. And then we will call, the first time we call, the b will become 4. The second time we come, we check, is it b equal 1? It is not, so we will run here again. So we will make this kind of function call. It means that the function will keep calling itself for how many times? So the second time it will call b minus 1. And b, since b become 4, we subtract 1, it becomes 3. And then it will come again and check. If this condition is not satisfied, then it will return again. So the function will call itself again. So, b minus 1, which means that 3 minus 1 equal 2. Okay? And then we will go again. So these two, is it b equal 1? Also no. But this will be the last time we do it. So b minus 2 minus 1 equal 1. So we will call it with b equal 1. And then once we come here, we find that b equal 1. So we will start returning a. So all this kind of function calls will keep returning a here. So for how many times? For actually this count. So it will call it for 4 times.
Right.
Okay.
Wait.
4 times.
Oh yeah, correct. Okay, correct.
And then we add a.
Correct.
So it become like 5. A multiplied by b. So this is how we make it. So you are not making a while loop here. You're not complicating your life. But it is heavy. It is heavy. Oh, okay, now say.
Isn't it unnecessary to have that if statement? The first one, B equals, like if B equals to 1, return A.
If you remove it, you will keep calling until your computer hang. And why it will hang? Because this kind of recursion is actually dangerous for the computer.
Oh yeah, because we didn't stop at 0. We don't have the okay.
Yes,
okay.
we don't have a stopping condition. This
Yeah,
is
yeah.
our safe valve to rescue the code from running forever.
Yeah.
Okay, so actually I
Okay.
don't want to complicate you, but that's why I'm telling you. But in short, this kind of calling will kill your memory because it will be
Yeah.
your this is more than the normal loop. The normal loop is okay. That this kind of call is different. Okay, so
Yeah.
okay, you know what's the main factorial?
Yeah.
Okay,
Like 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1.
excellent, good
Right,
in
yeah.
mathematics. Okay, so okay, if you look at the factorial, so if we talk about factorial, so you said 3 times
2 times 1.
Okay, and then so the last thing that we would like to actually multiply is when n equal 1, right? So if n equals 3, so we need to get 3 factorial, like here, n equals 3. So, okay, can you look at here?
Okay. Yeah, if n is equal to 1, return 1. Yeah, okay, correct. Because 1 factorial is 1.
This is the last thing that you need to run, right?
Yeah.
Okay, so see this? Our previous example was talking about factorial, that is, was not talking about factorial, but just talking about a multiplied by b. So here we're trying to find the factorial for n. So every time we will call it with a factorial that is less n minus 1. Okay, now, did you write this code, please? This one, please, did you write it?
Okay, I'll write it.
Still?
Hello?
Yes, can you? Done?
Yeah, done.
Okay, so it runs smoothly. What did you pass for A and B?
1 second, I am passing it through now. I accidentally put it wrong. Okay. Oh, I forgot to, that's why. I forgot to put the colon here. Now I need to move everything up. There you go. Okay, now okay, let's say I pass. So if I call mod and I pass, let's say 2 and 5. Done. I didn't print anything.
Okay, can you print and tell me if there is an output?
I'll put the whole thing in a print statement. Ten.
And you pass it A and B what? What is the values?
2 and 5. So yeah, correct.
2 or 5. Okay, yeah, that's good. So the factorial, so this is the form how the factorial should look like.
Yeah.
So, okay. So we return 1 when n equal 1. And then we say n multiplied by factorial minus 1. Okay. But then how this relates to n equal n minus 1 multiplied by n minus 2 until we reach 1. How is this related to this? Any idea? Any opinion?
I mean, it's correct. What?
Really?
It's. I mean, that is what factorial is.
Okay. Okay. Let's have a look. Can you understand what is doing? So this is the global scope where you call factorial 4. So
Yeah.
this is called the global scope. So once you
Right.
start, the first time you call when you pass 4 here, so you pass n equal 4. So it means that here we enter this function. We check, this is not satisfied, we come here. So here is presented by what? Return 4 and factorial 3. Is that clear?
Yep.
So it means that we call again factorial with 3. So we make another scope. We reserve a new place in the memory. Okay, typically in area called stack. Okay, and this stack get filled up fast if we don't really stop it. Okay, so once we call it with n equals 3, we come here again, we call with n equal 2, am I right? And we make another scope, n equal 2. And then we come here, we call with factorial 1. So is that the end? Am I right? So when should we get this?
Wait. Okay, yeah, so correct. So then they will stop and then you will just return 1.
So this return 1s here. So it means that here become 1. So 2 times 1 will be returned to this factorial. Okay. And this translate to this. So 3 times 2, because 2 multiplied by 1 is 2. And this will be returned to factorial 3. So it means 3 times 2 equals 6. So 4 times 6 will be returned to factorial 4. So if you have factorial 4, you print actually 24. Does this make sense to you?
Yeah, but it feels super like inefficient.
Complicated. It is okay. They say that this is not complicated from human point of view, but it is very harmful from the computer point of view. So computer does not like this kind of way. And also suppose we programmer also don't like it because it's not easy to understand. It is easy to misunderstand, and it's very hard to actually build the function this way, because you can make a lot of mistakes until you really build this kind of factorial calls or recursion calls. Okay.
Yeah.
Okay. Now, can you please write before we move on? So this is just simple. I mean, simple that you can have a template for the function. You always have if and else, and this have equality like that. Did you hear about Towers of Hanoi before?
No.
Okay.
Towers of Hanoi.
Yeah, it's okay. Don't need to rush for it. In the next coming slides, we will see what is. It is a very common problem in programming, and not only in programming, but they use it in programming books very many times.
Yeah.
Okay, done. We move to the next. So can you please, if you don't mind, just read this statement?
Actually, so can I go to the toilet first?
Yeah, sure. Yeah.
Okay.
Okay, so let me know, please. Can you read that statement?
Okay.
Is that clear to you?
Okay. Yeah.
Okay, then I will
It's
move.
kind of like it reminds me of like it. It reminds me of like math.power from Java. It reminds me of that, like its own method, kind of thing.
Okay, although it's slightly far from that, but okay. Yeah, maybe possible, yeah, because it, yeah. Okay, does these two functions or two methods produce the same thing? Is it?
Let's see. Yeah. And okay, the recursion one, the right side is what we've done.
Yes.
Makes sense.
Mhm.
Now the left side. Let I. Isn't this? This you will just keep multiplying up, right?
Yes.
Like
So
instead of going like 4 times 3 times 2 times 1, you will go up. It will be a multiple.
okay. So if you put here n equals 3, so it means that you are change values from what to what? From 1 until?
So if your n is 3,
Mhm.
then your I will go to 3 also.
So it will reach 3, right?
Yeah.
Okay. So it means that we keep multiplying this since I have 1, 2, 3 values. So it means that we keep multiplying to this production, which is at the moment have 1. We multiply for it 1 times 2 times 3. Am I right? Because this is what it is doing
Yeah.
here. Is that correct?
Yeah.
Okay.
Yeah.
So
Yeah.
okay. So it means that um, mm, mm. so and we will return production, which is the result of all this multiplication. And so it means that here is actually equivalent, totally equivalent to this piece of code. But in your eyes, I understand building this is complicated. But now, if you understand it and you look at it like this, you think this more readable, or this is more readable?
The recursion is more
Readable.
Yeah.
So okay, so that's why they say recursion may be simpler, and it may be efficient from the programmer point of view, but it is not efficient from the computer point of view. Yes, it looks
Yeah.
slightly simple and clear what is it doing, but this is if you know it. The first time you see it, of course, you have to think what is it really doing. Okay, so
Yeah.
please do. You already have done this. Am I right? Just write this, please.
Okay. You want me to write both or
No, only
just
one, because you already done this, suppose.
yeah. Okay. Almost done. The
Mhm.
okay. Okay. Return. Okay then.
Okay. Okay, this is the Towers of Hanoi. So if you have 3 tall spikes like that, and then you have a stack of 64 different sized disks. So you have disks that is looking like that, and they are stacked on top of each other like that. Start on one spike, and you need to move stacks to the second spike, at which point universe ends. Forget about this one. What is it? It's rubbish telling. So can we can only move one disk at a time, and a larger disk can never cover a small disk. So it means that we always need to put a large disk at the bottom and a smaller disk on top. So we need to actually move the whole disks from here to here. Okay, with one condition is that we only can move one disk at a time, and the second condition is that larger disk can never cover up a small disk. So you can never have something like this on a spike. So you always need to get the bigger one at the bottom, and then you put the smaller one on the top. So this is how it works. Okay.
Okay.
So any idea how this can be solved?
Oh, yeah.
So okay, that's good when you say yeah.
That
But
is easy, no?
you really? Okay, 64 disks is easy. Wow, they are optimistic.
Oh, 60. Okay, 64. The technically it means it will just take a longer time. It will just take super long.
Yes, a little bit long, yes. So, but if it is 3 only, it's easy, right?
Yeah, you just want it to be on C, right? You just want it all to be on C. Yeah, then you will just move.
So, okay.
Yeah, correct.
Can
correct,
you
correct.
recognize here if the
I've done this
movement is
before.
correct? Oh, really?
Yeah, okay. I do that, do that. Yeah, okay, okay, okay. Let me see here. Okay. 3, okay, that's correct. 4, 5, yeah, correct. Yeah, correct.
So it means that we take 7 steps to be able to reach our final destination, to just move it from A to C.
But it will scale exponentially.
Yeah. Okay. So okay.
So
The
4 will take like 23 steps or something like that. So 64 will take like so I don't know how too much.
Okay. So the thing is, if you want to make it in recursion, that is a bit tricky. Okay. Now let me see here. So he wants you to actually, as I said, do it in a recursion way. So he defined a method called print move, and then he passed it the two spikes, okay, and then and so this is supposed to be 3 spikes, A, B, and C, and then he make a so this is just a movement. So this is will just print. It will print that you moved from which place to which place. Okay, but the key here is that this is the issue here. So we know that when you reach n equal 1, so if you pass it with 3 disks, so you have 3 spikes, and then you will, once you reach n equal 1, you do the move. And this is the 3 different type of movement. But I will leave it for you to try it. I will not explain this at the moment. So what I will do is that I want you to try to understand. So this is just a basic understanding. So it means that you need to I will pass you the code. You need to try it. You need to print it out. And then you tell me what do you understand at the end, but not now. This is as homework. Okay.
Okay.
Additional to what you have, what you have left from maybe second or third time already. Okay. Agreed?
Yeah. Okay.
Okay. So I will just keep my mouth shut until your mother asks me about that, lah. Okay. Okay.
Okay.
So
Okay.
okay. Now, did you ever hear about Fibonacci numbers?
Oh, it sounds very familiar. It's the Fibonacci sequence or something, right?
Serious? Yeah.
Yeah,
Did
I've
you
heard
hear it
about it
before?
before. I've heard it
Okay,
before.
but you didn't see it, did you?
No, I don't remember where. I don't remember what I know it from. Yeah.
So this is also one of the common things that we are able to solve with recursion. So let us have a look here. Okay, so yeah, let me see here. Yeah, this one. So okay, this is basically the Fibonacci one. So look at this. This is the formula actually. So we say that every two, okay, so we start with basic two numbers like that, which is 0 and 1, okay? And we say which is f of 0 and f of 1. So we say that this number is the sum of the previous two numbers. So you add 0
Right.
plus 1, it give you 1. So this is, we come up, this is the third number, okay? This is the third. To come up with the fourth number,
Yeah.
we have to add the previous two, which is 1 plus 1. So that's why here it's 2. To come up with this number, we have to add 1 plus 2. So that's why it's equal 3.
Right. Then 3,
And so
5,
on.
8. Okay, 5, 8, 13. Yeah, 8, 13, 21, 21, 13, 34. Okay. Yeah.
Okay. So again, we are able. So this is the fixed formula for Fibonacci series. So it says that this n, so n equals 3, for example. So for f of when n equals 3, it means that you have here n minus 1, which means that it is 2 plus f. So this is what?
Wait a minute. Yeah.
For n equals 3.
Wait. Fn n minus 1. Wait, this formula doesn't make sense.
Why?
F. Okay, let's say f is 3. Oh, yeah. Okay. It makes sense.
Okay.
It makes sense.
Okay. So
Yeah,
okay.
yeah.
Now if I so what is n minus 2?
N minus 2 basically is because like 1.
Is f of 1, right?
Yeah, but
So
it makes sense lah. You're just checking which two numbers, because it has to be the two previous numbers that are added together to give you the third number.
yes. Okay. So f of 1
Yeah.
equal 1 right here, right?
Yeah.
So I put here 1. What is the value of f2?
Wait. Oh, wait. So the value of f2 is. Wait, why am I so confused? Okay, then technically the value of f2 is just 2 lah.
2? Really? It's this one?
I mean, if n minus 2 is 1, then n minus 1 is 2. Right? Sorry, it doesn't make.
So f of 1 is 1 and f of 2 is also 1. Am I right?
Oh, okay, I understand. It's like the index. Okay, I understand.
Okay, so how?
Okay, it makes sense lah. Yeah, so f of 2 is 1.
Okay, so it means equal.
F of
So
3 is 2. So equals 2.
like
Yeah.
that lah. Is it clear?
Yeah, makes sense.
Okay, so it means that we already make the formula to be able to get all these numbers, right? This is a formula.
Yeah.
Okay, are you able to write this formula in your code?
Yep.
Can you make it in a method that we are able to call it, and then if we call it, we pass it n, and it return to us f of n? Can you?
Okay. Okay. So I'll just make the method called Fibonacci, or what do you want me to
Yes,
call it?
yes, make it Fibonacci, yes.
And so f n equals f n minus 1 plus f n minus 2. Okay. So technically, I wrote down the formula already.
Okay, in a function?
Yeah, in a function. Then do you want me to put like if statements for if n equals 0 or something?
Mm,
Or
okay,
just leave
yeah,
it?
you can do that, yes.
Okay.
Because I believe you are not able to put these two. So your n can never be these two values. Am I right? Your n cannot be 0, it cannot be 1. It have to be
Yeah.
bigger than 0 and 1. It have to be bigger than 1, simply.
Yeah, yeah, correct, yeah. So, okay.
It's working. Did you print it out or see something working already?
Wait. Yeah, I get no error, but I need to print something out. Yeah, so do you want me to put if n is equal to 0, return 0, and if n is equal to 1, return 1?
Yes, it's better. That makes the function more robust, yes.
Okay. Then else return Fibonacci n minus 1 plus Fibonacci n minus 2. There's no match any update else. Oh, there you go.
Done.
Yeah.
Okay. Let us see how they do it in the recursion form. Yeah, we just take part of it and then let me see now. So newborn, so he tried to simulate how the Fibonacci works actually. So he said that newborn pair of rabbits, one female and one male, are put in a pen. Rabbits mate at age of 1 month. Rabbits have a 1 month gestation period. Assume rabbits never die. That female always produce one new pair, one male and one female every month from its second month on. How many female rabbits are there at the end of 1 year? So actually at the end, I understand that this is it's very hard to imagine. So it's okay. Now let me just put it again like that. Okay. So these two rabbits, they need to wait for 1 month. After they stay together for 1 month, then they will start to produce two small rabbits, one male and one female. And then after 1 month, they will grow, and then this original rabbit also produce another small one male and one female, and then suddenly these two male and female, they will after 1 month they will produce another small babies, male and female, and this original also still producing, and then so all of them now start producing, so the original is still producing. Okay, so you will find a lot of, if they don't die, then you will find a lot of things here. So
yeah,
okay, they want to say that okay, again they are still trying to simulate what this Fibonacci actually does. After 1 month, call it 0, one female. We have one female. After 2nd month, still one female, now pregnant. After the 3rd month, we have two females, one pregnant, one not. In general, this is the formula of the Fibonacci. They say females n, which is f of n, equal females minus 1 and females n minus 2. So it means that, again, this is fn minus 1, and here is fn minus 2. So he say that every female alive at month n minus 1, n minus 2 will produce one female at month n. So the female need to wait for 2 months until it produce something. This can be added, those alive in month n minus 1, to get the total life at the end. Just to make it short, this is he's using Fibonacci to be able to calculate this this story of rabbits.
Yeah.
Okay, and I think you already do it, but the key here is that you need to understand that for this specific Fibonacci series, if you want to write it in recursion form, then you have to know that your base cases, like you do just now when you put if statement, f of 0 and f of 1, they produce equal 1 equals 0. This is I believe wrong. Let me see here. So now are you able to say why here when x equals 0 or x equal 1, it returns 1?
Yeah.
Why?
Hmm. Yeah, shouldn't it only be because when x is 0, you should return 0. No?
Yeah, but why he's saying 1?
I don't know. Oh,
Okay, may I know if you put here, can you write this function?
okay.
And I want you to pass here x equals 3 and see what is going to be returned. Just now you already use in your own function x equals 3, right? Or you didn't?
In my own function, I used no. I mean, okay, I put 3 now. There you go. Now, then I get 2.
Okay, can you see if this function produces the same or not?
Okay. Hmm.
So what is the result?
And okay. The result is error.
Why error? Share your screen.
Question. Trace back most recent call last line 51. Okay. Module twin x Fibonacci x error name x not defined. But it is defined.
Okay, can you please share your screen? I want to see.
Oh, okay. Okay. Yeah. Oh,
Where is the error x? Okay, may I
error here.
understand? Okay, so from where you get this x?
From the code.
So x. Oh, okay. Wow.
Hmm.
Yeah, but I mean, you wait. You
Oh
put.
my god. Oh my god. Yeah. Okay, there you go. You don't get the same result.
Why? The question is why? Why we don't
Because
get the same? It
because
add one to it.
it adds one. No, I mean, I guess, but then it wouldn't, because either way, tree, x means tree, means you'll go to x2 and x1. Yeah, yeah, tree means it'll be x minus 2, x minus 1. So it should be 1 plus 1.
Mm-hmm.
So,
Something wrong here, huh?
or is it because, no, I don't know why. I don't know.
You give up?
Hmm. Hmm. Can I can I print X here? Does that work? Does that work? Print X. Wait, wait. If I want to print one X here, will that one even work? Will these ones even work? Okay.
Try.
What happens? Okay, you can go away. I can go away. Okay. Hey, this one also can go away. Huh. Can't print X there. Oh, that makes sense. Print X here.
Because you put it after the return, right?
Yeah. Oh. Wait, what? Wait, what? Why is it now invalid syntax? I didn't even change that.
Okay, so you cannot put a print statement after return because it will never be seen. The
Right.
code stopped
No,
at the return. So you have to put it
that
before
is
the return. Yes.
true. That is true. But so all of this, why does all of this turn
I think
what?
maybe
Oh, it's because
your
oh
indentation is not perfect.
yeah. Okay, but why is this? Oh, the return. Okay.
Same, you cannot put anything under the return. You have to put it before the
Yeah.
return.
Yeah.
And
Oh,
also the indentation.
yeah. Now it's in the okay, makes sense.
But you have to, you cannot print X this way and this way. This will be mixed up. You have to say, this is a
Yeah.
base case X, base case X, and maybe leave the other one X like that. So you have to differentiate. If they both print numbers, you will never try to.
What?
You don't use a single quotation. You have to use double quotation.
No, it's because I put a
Okay, he
plus.
accepted it.
Yeah.
Okay.
Yeah. Yeah. Okay.
Mhm.
Wait, what? 3.
This is 3 from your previous printing. Did you comment? You already comment. So he printed 3 out. Mhm.
I'm here.
So when you pass your first X, he print out 3 because this is 3. X the first time it
Yeah.
enters 3. Okay. And then the second time you call it also, it is 2. Because here, so you pass here 3 minus 1, which is 2.
Correct. No. Oh yeah, 3 minus 1 is 2. Sorry. Yeah. So X will be 2.
So this will result in actually this is to be printed.
Hmm. Right. I see.
And these two, well, will make another 2 calls. One for Fibonacci when it is 1, another when Fibonacci equal 0. So that's why you see these two. So this, it will not make another calls inside, but this is 2. So 2 is still large. You need to reach 1 or 0 to be able to end. So these two belong to here. Sorry, here. And these belong to here. And this 3 is actually the final addition of all the returning from here. So this return 1 and this return 1, this another one is added from here. So it means that at the end, this is like, but the problem here that this is actually does not work with exactly the same Fibonacci mathematical formulas that we already studied just now, right? So we discuss this next time, but okay, I want you to. So how much time remaining? How much time we have?
It's already 8:43. So
Do we
we are
have
out
time?
of time.
Out of time this time? Okay.
Yeah.
So
Out of time.
you manage to skip this time for the quiz. Suppose as per your mother request that every time she need to see your progress. It seems that she's so worried about you. So, Okila, what to do? Then we stop here now.
Yeah. Okay.
Okay. See you next class. Can you please revise so that the result does not show that you are doing something wrong?
Yeah.
You know, did you see your results?
Yeah, I
Why
read
is
through
it
it.
12?
Yeah, I read through it.
Okay.
The
Hopefully this can
the
improve.
the level, I accidentally put a B there.
Okay. And there is a lot
Made a
more to
typo.
also. Yeah.
Yeah, there's some other.
So,
Yeah,
okay.
yeah.
Okay. You will check your slides, please.
Yeah.
Okay. Then see you next class. Take care.
Okay. See you.
Bye-bye.
Bye-bye.